Welcome back to our series on electricity and magnetism. In this episode, we're going to talk about charge. Charge is fundamental to the study of electricity. In essence, charge is responsible for one of the four fundamental forces in the universe, that is, the electrostatic force. The electrostatic force is the force of either attraction or repulsion between either like or unlike charges. Charge comes in two particular flavors. There's positive charge and negative charge. We tend to use the mathematical symbols for these, but there's nothing negative about a negative charge, nor is there anything positive about a positive charge. These are simply labels. As I indicated, the fundamental force, electrostatics, occurs entirely as a result of charge. Like charges repel. So two positive charges would have a force that would send them apart. Similarly, two negative charges would also have a force that would send them apart. However, two different charges, plus and minus, would instead feel a force of attraction, each for the other. For a long time, charge was deemed really mysterious before we really understood the subatomic structure of an atom. And charge is fairly well understood now. What we need to do with charge is look at how it interacts with other matter. Turns out there's two really important kinds of matter we're going to examine. The first is called a conductor. Whenever charge interacts with a conductor, it does so in a way so that it can flow. Conductors tend to be made of metals or metallic alloys. And their virtue is that they have mobile charge. They have the ability for charges to rearrange themselves. So due to the property of like charges repelling and the fact that conductors allow charge-free movement, the following would happen if I place charge on a sphere made of a conductor. The charge would all find its way to the surface. That is, it would work itself as far apart as possible. Because if any two charges were closer together than they necessarily needed to be, the force of repulsion between them would drive them apart. Now, if I remove any excess charge, the conductor, of course, is made of atoms, and atoms have equal number of positive and negative charges in them. So most materials are electrically neutral. That's why the electrostatic charge is really hard to detect unless we increase or decrease the natural number of charges on a surface. But if we do that on a conductor, what we'll find is the charge flees all the way to the furthest edge of the surface. It is impossible for a conductor to do anything else than store its charge physically as far apart as possible. The other kind of material we'll be interested in is called an insulator. Insulators tend to be made of plastic or glass or rubber. They're organic molecules that are covalently bonded. As a result, they have access to very few free electrons. The electrons tend all to be tied up in bonding. As a result, charge is very immobile on the surface of an insulator. If I had a sphere that was made of insulating material and I took and placed charges at various different locations on it, those charges would stay put. That is, the charges themselves are immobile because the material itself provides them with no conduit, no ability to move. Just like a conductor in its uncharged state, an insulator would have just as many positive and negative charges. After all, it's made of atoms, and atoms are electrically neutral. But if I were to add excess charges to it, those charges would not be mobile. We would not see them fleeing to the extreme edges, which means there's naturally a tension in an insulator because there are forces closer together than they necessarily need to be. We'll be looking more at conductors and insulators later. What we want to focus on right now is, what is this mysterious electrostatic force that exists between charged particles? Well, it was quantified not too long ago, and today we call it Coulomb's law. And Coulomb's law is that the force in between two charged particles is equal to 1 over 4 pi epsilon naught times Q1, Q2 being the measurement of the two charges, divided by the radius between them squared. Coulomb's law is an inverse square law, and that means the force goes as an inverse of the square of the distance. Coulomb's law is also directly proportional to the size of the two charges. Well, let's take a look at the units that this Coulomb's law is measured in by examining each element of it. First, there's the force itself. First thing to recognize is that it's a vector. It always points along the line between the two charges, and it's either attractive or repulsive based on the nature of the two Q's. The unit, of course, for force is the Newton. The charges themselves are measured in the standard unit of charge, and the SI unit for charge is the Coulomb. Sometimes it uses capital C as its symbol, and of course the Newton uses capital N. Third, of course, is the radius. The radius uses meters as its standard symbol, although we will frequently measure it in units that are much larger or much smaller than that. The final thing is this 1 over 4 pi epsilon naught, and what it does is it converts the units that both the charges and the radius is in order to make newtons. It also acts as a numerical multiplier so that the units of meters squared and coulombs actually give us the correct size of the Newton force. The size of epsilon is going to give you a really good idea about the size of the electrostatic force in comparison to the size of the charges. E naught is known as the permittivity of free space, and it actually has a value of 8.85 times 10 to the minus 12th, and its units, of course, are coulombs squared per Newton meters squared. Because if I place those units here, it will cancel the Coulomb squared, cancel the meter squared, and end up giving me units of newtons for the force. Now notice how small this physical constant is. This constant is little and is in the denominator, which means it's functionally going to act as a number that's about 9 times 10 to the 12th. That's a colossally huge number. So even if these charges are quite small, and if the radius between them is modest, we're going to get very, very large values for the Coulomb force in between two charged particles. So there's Coulomb's law. It's a fairly easy plug and chug scientific formula because it's a vector formula. If we have more than one charge that's being acted upon, then we necessarily will need to calculate the resultant vector force, and that means doing vector addition. So the vector addition that we covered in the last episode will definitely be key and important here. Well, the final thing we want to talk about in regards to charge is the idea that charge is quantized. Quantization has influenced physics in two ways. First, it's invented the whole field of quantum physics, which is based entirely on the idea that energy is quantized. We already knew that matter was quantized. Chemistry expresses that matter is made of atoms, and atoms come in smallest units. Well, it turns out that the atoms themselves are made up of charges that are quantized. The smallest unit of charge is the electron. The electron has an amount of charge equal to E, and it's the fundamental charge. It's 1.6 times 10 to the negative 19th coulombs. It turns out that there's no way to get an amount of charge smaller than this because you can't divide an electron into a smaller unit. As a result of that, charge comes in these very, very tiny packets. A proton uses this symbol, and it simply has a positive E worth of charge. An electron's charge, of course, would be a negative E, and a proton's charge would be a positive E. It would be 1.6 times 10 to the negative 19th coulombs. And that's why all atoms are electrically neutral. They have the same number of protons as electrons. And of course, all protons and electrons have exactly the same amount of charge. They just have opposite amounts of charge. That's really what holds the atom together. The electrons are attracted to the protons, and that's what holds the atom cohesively. So charge is quantized, and these are the smallest units of charge we can have. When you gather charges together and you have two piles of charge, those piles of charge are going to exert a force on each other, and that force is proportional to the size of the charge piles divided by the radius squared, multiplied by this constant, and that will give you the Newton force between those two piles. And then finally, charge interacts with matter in two ways. We can charge a conductor or an insulator. In the case of a conductor, the charge will always flow to the surface. In the case of an insulator, it will always stay where you put it, because that's the nature of conductors and insulators. And the final piece, of course, is that charge comes in two varieties, positive and negative. Like charges repel, and unlike charges attract. Charge really forms the backbone of our entire analysis of electricity and magnetism. This first unit is simply designed to get you familiar with charge and to work with the numerical analysis of charge.